All right, welcome back. I haven't heard from anybody. I think I said I was going to send out homework through Canvas last time. I did. If you didn't get that information, please let me know. I'm going to pick up where I left off last time. We started electromagnetic theory and just a little bit of background material to start with. Um, Today we'll get more into the nitty gritty of the topic. I am going to present E&M in a form given by Holton Haskell. In a book called Plasma Dynamics. And that was published in 1965, actually before my birth, but it's a very good book. It gives a good representation of the topic, and what I give you in class here should be self-contained. Okay, so if you think some information is missing, please ask and I'll make sure that you have it. All right, so let's get started. The force on a charged particle. As a result of electric and magnetic fields. Is the Lorentz force. Everybody heard of it? About half the class, okay. We have a force vector, and we will write this in terms of charge on the particle, Q. We will divide by the particle mass, M. If we take that ratio and multiply it by the electric field vector plus the particle velocity crossed with the magnetic induction, or magnetic field, people usually call it. I'm just going to call this 2-1. This is equation 1 in that chapter of Haskell, but it'll help us refer back to things. Okay, so I had a crazy physics professor when I was in college, and I never ever forgot this because he told me the corniest thing I've ever heard. I don't know, you're all too young to probably remember Muhammad Ali. Do you remember who that is? Okay, he was a heavyweight boxing champion back in, I guess, early 70s. And he always used to, his catchphrase was like, float like a butterfly, sting like a bee when he was fighting. So I had this crazy faculty member in the early 90s, a physicist, when I was taking electricity and magnetism, and he would say, float like a butterfly, sting like a bee, the force on a charged particle is Q times E plus V cross B. And I never ever stinking forgot that. It was so stupid. It's kind of like a bad movie sometimes. They're so good, they're entertaining. So hopefully that'll help you remember this. Okay, the electric field. Excuse me, E. And the magnetic induction. is a vector. Call that B. I'm not going to get offended if you call that the magnetic field because most people do. These satisfy Maxwell's equations. Okay, and those are, we start with Ampere's law. We have the curl of an H vector. That's the magnetic field strength. It's related to the B field through a constitutive relation we'll talk about later. So the curl of H vector is equal to a total current vector. And so that is J, which is the current density, amps per square area, or per area. And then we have a displacement current term, which is the time derivative of the electric displacement vector. And we will define these shortly. Call that equation 2. Then we have Faraday's law, which is the curl of the electric field. And that is equal to the negative of the time derivative of the magnetic induction. Then we will have Gauss's law for the divergence of the electric field. That's written as the divergence of the electric displacement. Again, we'll define that shortly. That is equal to the charge density, which is the number of charge, the net charge per unit volume. And then we have Gauss's divergence law for the magnetic field. Everybody's probably heard divergence of B is equal to 0. Until Sheldon Cooper discovered it on Big Bang Theory, right? I thought that was interesting, that reference on that show. Okay, so this D vector is the electric displacement which we'll talk about in detail. And this Q bar, that's not a vector. Q bar is the charge per unit volume. J is the current density produced by a charge in motion. Oftentimes, though, you'll hear that people refer to that as the current density that results from convection of charges. So that, well, I skipped an equation. This is equation 7. This Q bar up here. Oh, I guess I could move it up so you can see it. There you go. Q bar is equal to the sum over all of the particles, or the species, I should say, of the charge on per particle on that species times the number density of that species. So that would be the number of charges per volume. So you multiply the two together, you get charge per volume. And then the J vector is given as current density is equal to the summation over the species of the number density of the species times the charge, the particle of the species, so that is just U bar, right, times an average velocity for the species. Okay, so here we have where this v sub I and in between the less than and greater than signs is the mean velocity of species I. Okay. So we are going to now consider some arbitrary volume, we'll call V, that's surrounded by the, or defined by the surface, we'll call S. Okay, and we will have a current leaving that volume. And so the current leaving volume V across the surface must be equal to the change of the charge within the volume. So it's just basically a continuity of charge. And so what we will do is take the time derivative of the charge in the volume. So we'll integrate over the volume. And so we're looking at the charge in the volume. We'll take Q bar, the charge density, and integrate over V. And that has to equal the negative of the charge entering or leaving the volume through current. So we'll integrate over the surface of the current density dotted with a unit normal to the surface times some differential area, d sigma. Okay, using the divergence theorem. And in case anybody's rusty on their vector calculus, that is, we have a surface integral over some vector dotted with a unit normal to the surface, dA is equal to the volume integral of the divergence of that function dB. Okay, so using that, the divergence theorem, we obtain the following for equation 2.8. The time derivative of the charge density is equal to the negative divergence of the current vector. So this is the equation of continuity of charge. It also can be derived from Ampere's law. This is just a little bit more straightforward. Okay. Current arises from the net transfer of charge. This can result from mass motion. Or the motion only of charged particles induced by Lorentz force. Okay, in this situation, this can lead to a linear relationship. And that is that the current density is equal to a conductivity tensor times the electric field. Okay, so here, the sigma tensor is the conductivity tensor. To be more specific, the electrical conductivity. Okay, for a isotropic plasma, the conductivity tensor is scalar. And this relationship reduces to the current density being equal to an electrical conductivity, that's scalar, times the electric field. Okay, this is the familiar Ohm's law. And if you look at the units on this, J will have currents of current per meter squared. Electrical conductivity has units of 1 over ohms times meter. And the electric field is volts per meter. So essentially you have V is equal to IR, or in this case we have I is equal to 1 over R times V. Okay, so things become a lot more complicated when you're looking at current flow through a gas, a plasma. But we still haven't talked about that displacement vector, the electric displacement vector. And that involves dielectrics. Dielectrics consist of balanced charges which can be displaced by electric fields. So let's say we have a positive and negative charge bound in the dielectric, and we apply an electric field to it. So if our electric field is in that direction, the positive charge is going to want to go along the positive direction of the E field, and the negative charge will go in the opposite direction. And they may move apart to some distance that we will call an R vector. And let's say that there's a surface in there that we're interested in considering. And it'll have a unit normal vector to that surface. When we apply the electric field, the charges separate and then across at least one of them crosses the surface. So you have a move or a change or flow in charges as a function of time, and that is essentially a current. And if we look at that surface, smaller version of that over here, and call that VA during some over that distance R, you'll get a volume. Right, so this will give us a dV or unit normal vector to the surface there. Okay, so now that we've drawn these pictures, we can discuss this better in more detail. The displacement of the bound charges results in a dipole moment. And that is the charge, Q, times the vector of separation, R. Thank you. I better be more attentive. You can start throwing at me stuff at me soon. So, okay, so we have this dipole moment. And we can also define a dipole moment per unit volume. Okay, and so we will say that is the number density times Q times R vector. The charge which crosses a unit area, that VA, due to the displacement is the n times q times r vector dotted with the unit normal vector to the surface and dA. So this r dotted with the unit vector dA is basically a dV, differential volume element. Okay, so that's how much charge crosses the surface. And the net charge crossing the closed surface S, bounding the volume. So volume is V, and this is equal to a net charge, we'll call capital Q, is equal to the integral over the surface of the n times Q times r dotted with the unit vector normal to the surface dA. Okay, since the net charge originally in the volume was 0, that we have basically same number of positive and negative charges within the volume to start with. Then a net charge will be left within the volume. That is equal to what we'll call minus capital Q sub P. And this is called the polarization charge. So Q sub P is equal to minus of the surface integral of n times Q times the r vector dotted with n hat dA, and that is equal to the negative of the surface integral of a capital P vector dotted with n hat dA, called equation 13, and this equation defines the polarization. Which is this capital P vector. So that capital P, or polarization, is equal to n times Q times the r vector. If we assume a linear relationship between P and E, Okay, so the polarization depends linearly on the electric field, and we will write that as the polarization is equal to a constant called epsilon naught times a tensor alpha times the electric field vector. And here, the epsilon naught is the permittivity of free space. That will come up a lot in the work that we do going forward. And this alpha tensor is the electric susceptibility tensor. And you can look up epsilon naught. It is a fundamental constant. Has a value of 8.85 times 10 to the minus 12 with units of farads per meter. And if you break that down into MKS units, that is the same as S squared or second squared per meter squared. And I will be posting a cheat sheet that takes all of these E&M units and converts them back down into the MKS system, so that if you ever want to do a units check, you can. And it's really useful and powerful. All right, so now finally, the electric displacement vector is defined by D vector. The electric displacement is equal to epsilon naught, permittivity of free space, times the electric field, plus, most people will stop there because they're ignoring the polarization. Or they're writing this in a little bit different form that we're getting to later. Equation 16. Okay, so now using equation 215, we have the following. The electric displacement vector is equal to epsilon naught times E plus epsilon naught times the electric susceptibility tensor times the electric field. This is equal to epsilon naught times the identity vector, so just the diagonal one, everything else zero in the matrix, plus the electric susceptibility tensor times the electric field. This is further can be written as epsilon naught times a kappa vector, or vector tensor, times the electric field vector. Call that equation 17. And we have this kappa tensor, which is the identity tensor plus the electric susceptibility tensor. And this kappa tensor is called the dielectric tensor. And the I tensor is the unit tensor. If the medium is isotropic, then the dielectric tensor is a scalar, kappa, called the dielectric constant. And the quantity, epsilon, is equal to epsilon naught times the dielectric constant, is called the permittivity. Okay, so now if this polarization changes in time, a net current must flow. And the total current density is given by capital C vector is equal to the current density J plus the derivative of the electric displacement with respect to time. And this time derivative of the D vector is called the displacement vector. And one way to think about that is to think about a capacitor in an electric circuit. When you don't have an electric field sitting there, all the charges are in equilibrium with between the two conducting plates. And when you apply an electric field, the charges separate, go to the plates, and after the separation is done, the current basically stops flowing, right? So that is basically this displacement current term. Okay, so those are electric properties associated with a medium. Now let's talk about the magnetic properties. And These are described in a manner analogous to polarization. Okay, let's start by looking at an orbiting electron. And it produces a magnetic dipole moment. Equal to the current I times the area of the orbit. Okay, so this magnetic dipole moment we'll call a lowercase m vector, and it is equal to some current that is multiplied by the area normal to that orbiting charge. So if we have I going this way, we would have an electron orbiting in the opposite direction, and the area that we're interested in is the area of that orbit, and hat is just the unit vector normal to that. For a circular orbit, and an orbital frequency of omega divided by 2 pi, the current is I is equal to the charge on the electron, or charge divided by the period of revolution, and that is equal to Q charge times the frequency F, so the frequency like in hertz, and that is equal to the Q times omega over 2 pi. For this case, then the magnetic dipole moment, lowercase m vector, is equal to Q times pi r squared over 2 times the unit vector normal to the surface, n hat. Now we're going to define something called the magnetization vector. And this one is a capital M vector, and it is the magnetic moment per unit volume. And so this is defined as the number density, capital N, times the magnetic dipole moment.
What's it?
What's the capital N?
N.
Oh, N is the number density. So you would have so many per unit volume. Okay, so now we can define the magnetic field intensity H vector. Which is defined by the following relation. The magnetic induction vector B is equal to a fundamental constant, mu naught, times the magnetic field intensity plus the magnetic moment, or the magnetization vector, excuse me. Magnetic moment's the little one. After a while, you get into definition overload when you're going through this stuff. Okay, so here, this constant mu naught is a dimensionless constant. And I want to make sure that I qualify that and say in MKS units is the permeability of free space. And so mu naught is equal to 4 pi times 10 to the minus 7. And it is unitless. All right. So the relation between H and M. Is linear. Or I should say, if it is. We like to pretend everything's linear. Makes life easier until it's not, right? So if there's a linear relationship between those, we have that the M vector is equal to a chi tensor times magnetic field intensity. And this looks a lot like the position of the electric field susceptibility or a tensor. Then here it is the chi tensor is the magnetic susceptibility tensor. Okay, so this gives the following. The magnetic induction vector B is equal to the permeability of free space times the identity tensor plus the magnetic susceptibility tensor times the magnetic field strength, H. Or we have magnetic induction is equal to mu tensor times H vector. And here, the mu tensor is the permeability tensor. Okay, we're almost done with definitions. So we've done the electric field properties, we've done magnetic field properties. Again, this is just like the permittivity of free space. If you have an isotropic medium, that becomes a constant. So then you have B is equal to mu times H. Okay. The electromagnetic vectors. We have introduced or summarized. So this E vector is the electric field intensity. So it has units of volts per meter, which is can also be written as kilograms times meter per coulomb second squared, which can also be written as newtons per coulomb. And again, I'll give you that cheat sheet I was talking about so that it's easy to do your units, checking your units and problems. Okay, B vector is the magnetic induction. It has units of Webers per meter squared, which is also given as units of kilograms per coulomb seconds, which is also Newton seconds per kilogram meter, which is also Tesla. And you also get Gallisons in there, and there's a whole bunch of variations or combinations of those. The J vector is the electric current density. So we have amperes per meter squared. And the ampere is a coulomb per second. So we have coulombs per meter squared second. Polarization vector, P. Has units of coulombs per meter squared. The D vector is electric displacement. Coulombs per meter squared. The H vector is the magnetic field intensity. So amps per meter, or also coulombs per meter second. Okay, so these are all part of Maxwell's equations in some way or another. And we've already written down Maxwell's equations in one form. Now we're going to head towards another form. So Maxwell's equations are mathematical representations of experimental laws. We define some flux and force terms. These are defined on a surface S. Bounded by curve C. With surface normal n hat. So basically, we have some surface dA. It has a unit normal and hat. There is a closed surface or curve C that defines that surface, and some length along that surface is ds. dA is a small element of that surface. The whole surface has area A. First thing we're going to define is the magnetic flux. And that is equal to the integral over the surface of the magnetic field dotted with the unit vector normal to the surface dA. Now we'll define the electric current flux. That is equal to the surface integral of the total current C vector dotted with n hat dA. We will define the magnetic force as being the closed integral about the curve C of the magnetic field intensity H dotted with ds. And then we have electromotive force. And that is equal to the closed integral about curve C, and that is the electric field dotted with ds. So now, Faraday's law can be written in terms of these. We have the time rate of change of the magnetic flux. So d by dt of the surface integral of B dotted with NDA is equal to the negative of the electromotive force. So it's equal to the negative over the closed integral about curve C of the electric field dotted with ds. So basically this in words says a change in magnetic flux through a surface is accompanied by an electromotive force on the boundary. Okay, now Ampere's law. Oops. Eraser. For this one, we have the surface integral of the total current dotted with n hat dA is equal to the circuit or closed integral over curve C of H dotted with ds. In words, this is the current flowing through a surface S is accompanied by a magnetomotive force. On the boundary. Okay, and I think about what Ampere and Faraday did. The guys had to be geniuses to take a bunch of data that they just kind of observed and come up with these laws. So these are integral forms. What is typically or more commonly seen is the derivative form or differential forms. But before I get to those, I want to close this section just by saying direct application of Faraday's and Ampere's laws is often an effective way to obtain both quantitative results and detect errors in complex models. Similar to the use of conservation of mass, momentum, and energy. And fluid mechanics. Very powerful. And the next time, we don't have enough time to get into this, we will talk about the differential form. And I think I fooled Mark. The differential form of Maxwell's laws is next time. Okay. Have any questions about the homework or anything we've discussed in class today? Don't hesitate to contact me. I know for most of the engineers taking this course, this is the first time you've seen most of it. And I introduced this material because it is a fundamental part of plasma physics, and you cannot do electric propulsion without having some understanding of those fundamentals, at least where things come from. Anyway, have a good weekend.